of my presentation. So basically, we're evaluating a network of low-cost sensors that are able to monitor multiple pollutants. And we're doing this to examine the fine spatial scale exposure disparity. And we wanted to do it in an urban area. So we're doing it in the Minneapolis-St. Paul metropolitan area. Okay, so this is the outline of today's presentation. I wanted to talk a bit about what motivated this project and introduce low-cost sensors versus the traditional air quality monitoring methods that we have, and then briefly go over the sensor network that we're analyzing, take a look at the data set, and then jump into results and conclusion. So we know air pollution is the single largest environmental risk to human health. And according to the World Health Organization, just in the year of 2019 alone, there have been 4.2 million early deaths globally. So we're especially concerned about urban air quality because of the population density within an urban region, as well as the variety of emission sources that we have concentrated within an urban region. So due to the uneven distribution of emission sources that we have, the pollutant concentrations can vary significantly over small distances. So this is why we're looking into high spatiotemporal resolution in air quality monitoring, because this can tell us whether there are disparities in air pollution exposure to specific pollutants, especially within an urban region. So for instance, we can take a look at whether there are hotspots, pollution hotspots from like local emission sources, or we can see like whether there are temporary pollution peaks. And I also wanted to talk a bit about the air quality in Minnesota. So the study region is in Minnesota. So their air quality is good overall and is currently meeting all federal standards, but that is overall, but there can still be health impacts because we don't know how it varies from location to location. So, currently, the traditional way of measuring air quality has been using federal reference method and federal equivalent method grade instruments. And to meet this criteria, you have to go through a strict protocol and testing of performance. So it's safe to say that the data is very accurate, but the downside is they can be very expensive, ranging from about $15,000 to $40,000 per monitor, according to the EPA. And because of their high operating cost, and also because they're kind of inflexible in terms of siting, having to build like a large infrastructure to house the equipment, and also needing temperature controlled structures, we can only install a limited number of these instruments, which creates like a very sparse network. So comparing with that, the low-cost sensors, the purchase cost is only like a fraction of this price. And there is more flexibility in terms of siting because it's more compact and portable. And you don't need much training to operate it, but there might be the need of some skills to interpret the data. So because of their low cost, we can deploy a larger network, a larger number of sensors, meaning like a more dense network. Okay, so the sensor network that we're evaluating was established under the Assessing Urban Air Quality Project, which was led by Dr. Monica Vidali at the Minnesota Pollution Control Agency. So they have 45 sensor sites in the Twin Cities region, and there is at least one sensor in each zip code. So in this study, we defined fine scale to be from zip code to zip code. And they use AQ mesh pod sensors, and there have been a large number of academic studies that have used these sensors, and they have also like numerous global co-location comparison trials against reference stations, meaning that they're going to set up like a AQ mesh sensor next to a reference sensor, and they're going to see the correlation between the readings. Okay, so this is the network that we have. And as you can see, the site number 4 is highlighted in red because it's located outside of Minneapolis-St. Paul, so we excluded it from our study. So in our study, we have 44 sites, and we evaluate 7 pollutants: particulate matter, carbon monoxide, ozone, nitrogen dioxide, NOx really, and sulfur dioxide. So the monitoring duration was 2 years, ranging from June 2019 to June 2021. And the readings that we get from the sensors are readings every minute, but we average these to get a data point for every hour. And we have received concentrations in parts per billion and particulate matter in micrograms per meter cube. Okay. So this is the first analysis that we did, which is a time variation plot of concentration. So we wanted to investigate both the seasonal and daily variation. So when looking at the seasonal variation, we binned the concentrations into 15-day bins, and we calculated the median concentration for each. The medians were taken to avoid the influence of outlier values and extreme values. And because the 15-day medians were plotted, we were able to see the trends more closely and more clearly. And we used shaded error bar plots to show these variations because we kind of wanted to see the general distribution of the concentrations. So we've plotted the quartile 1, the 25th percentile, and quartile 3. Okay, so this is the seasonal variation of CO, which is very interesting because we're seeing a winter high and a summer low. And this can be explained because in the winter, you have more heating. So this explains why there's going to be a high concentration in the winter. Whereas in the summer, carbon monoxide is an ozone precursor. So it's going to contribute to the formation of ozone. So we can assume that maybe carbon dioxide is being consumed in this portion of the graph. And we have all 3 years plotted in the same graph. And moving right along, when looking at the ozone, it kind of, the carbon monoxide graph kind of makes sense. And we see that there's a spike during the summer when there is more photochemical activity under more sunlight, and as expected, like a winter low. So this is very typical for ozone. So, okay. So looking at PM 2.5, we don't really observe a significant variation, but we do notice that the trends for PM 2.5 and PM 10 are quite similar. So yeah. And then looking at NO2, we do see a summer high that is not typical because we would expect the peak to be during winter heating. But we noticed that there is also a similar peak for SO2. So these trends are quite similar, which was interesting. Okay, and then we move on to the daily variations. And for CO, we would expect there to be peaks during rush hours, like from 7 to 8 a.m. here, and then kind of decreasing maybe during the daytime under photochemical activity. And then ozone, we can see 7 to 8 may be the rush hour, and then you have all sorts of NOx and VOC emissions, and then under sufficient time in the sunlight, you see ozone being formed. Okay, and then PM 2.5, again, we don't see much of a significant variation. Same goes for PM 10. And then NO2 is kind of interesting because we see like a double peak trend, which is kind of similar to SO2. But I think an important takeaway from this would be that all the results that we see for all 3 years, they all kind of follow, for each pollutant, they follow like the same basic kind of trend. So that was kind of interesting in terms of sensor performance, which reassured us. Okay, so the next part of the analysis was to look at spatial variation. So for this, we calculated the coefficient of divergence. This tells you whether there's a significant difference among the concentration from site to site. So we're comparing site pairs, and the COD value computed can range from 0 to 1, 0 indicating that there's not much of a difference between the concentrations, and then 1 indicating extreme differences. So based on literature, we took COD value greater than 0.2 to indicate significant spatial heterogeneity. And the concentrations were hourly concentrations. And then for this analysis, we only considered the sites having readings for every hour of 2020 to compare each of the hourly concentration points. Okay, so these are the results from the coefficient of divergence analysis. And for NO, we observe strong spatial variability, and it's ranging from a moderate value of 0.2, which is the threshold value, to 0.65. And then moving right along to CO, we see that the highest COD value computed is 0.17, which is lower than the threshold. So it's safe to say that this is a very weak spatial variability. So for ozone, we see that it ranges from 0.08 to 0.34. So it's spatially homogeneous to a modest spatial heterogeneous distribution. And then PM2.5, maximum COD is 0.13, so low spatial variability, and low to modest spatial heterogeneity for PM10. And then again, similarly, spatially homogeneous to somewhat modest spatial variability for NO2. And then for SO2, we observe weak spatial variability with 0.11 as the maximum COD computed. Okay, so the next analysis was source characterization. So for this, we use the conditional bivariate probability function. It's easier to say CBPF. Okay, so this is a combination of the basic CPF function and the bivariate polar plots. So the basic CPF function gives you the probability that a high concentration is associated with a given wind direction. So it gives you source directionality, whereas the bivariate polar plots can be used to display a concentration in terms of both the wind direction and wind speed. So when you combine these together, we can find the probability, find an estimate of the probability that high concentrations are corresponding to a given wind direction and speed. So using this, we're able to determine source directionality. And we're also able to distinguish whether this source, the source that is contributing is a local source, or if it's a distant source based on the wind speed dependency. Meaning, if you have a very high concentration at a low wind speed, or like stagnant conditions, you can assume it to be an emission source within that local region. Whereas if you're seeing a very high concentration under a very high wind speed, then you can assume that it's being transported over a distance. So in this analysis, to determine high concentrations, we chose a 75th percentile threshold. And we generated plots for all 7 pollutants for each season of 2020. So 28 plots altogether. And to do this analysis, I followed the work of David Carslow and also gave reference to a study by Dr. Hopke and Avod in 2021. And this was done using the open air package in R. And for the wind speed and wind direction data, we used the CISL Research Data Archive and used the data for the Minneapolis-St. Paul International Airport Station. So this is, I just wanted to show what these figures kind of look like. Let me see if I can annotate this. Okay, so in this radial dimension, you see the increasing wind speeds. So towards the center, you have low wind speeds. Towards the outer side, you see higher wind speeds. And then this also shows you the direction. Okay, so let me find this. Oh, my bad, sorry. Okay, so this was for PM 2.5 in spring 2020. And you can see that the emission is contributed from a source over a distance. And you can see it's coming from the southern direction here. And when we look at fall, we see that it's under low wind speeds, and the source is probably a local one. Whereas this one is, we're seeing high concentrations under high wind speeds. So the interesting thing here is that we kind of observed the similar type of pattern for PM10 in the spring and the fall. So in the spring, it's being transported from somewhere, whereas in the fall, it's a locally emitted concentration. Another interesting finding here is that if we look at SO2, in the spring, you see contribution from local emission sources. And in the summer, it's being transported from somewhere with the high concentrations and high wind speed. And in the fall, again, you see the contribution from local sources. And in the winter too, you see contribution from local sources, meaning that only in the summer, it's being transported from somewhere. So I kind of want to go back to, kind of want to go back to this plot here. So we saw an unusual summer high for SO2, and we noticed a similar trend for NO2. And then when we come back to this, we see that in the summer for SO2, we're seeing contribution from a distant source. And interestingly enough, we see a similar pattern for NO2 as well. So our interpretation for this is that this might be due to the Canadian wildfires, which is contributing to these summer peaks. And then the next data analysis we had was the power spectra analysis. The idea here was to find dominant periodic cycles within this time series data of concentration. And to determine the dominant cycles, we looked at the spectral density values. This was done in the MV spec package in R. And we looked at the data over the entire period, but we separated it into 8 seasonal subsets, so ranging from summer 2019 to spring 2021. And we gave reference to the work of Marinescu in 2019. So these are the results summarized from the power spectral analysis. And this is interesting because we see 15-day cycles, which is half a month. We see daily cycles of 1 day, and we see 30-day monthly cycles, as well as a month and a half, 45-day cycles being prominent in most of the seasons. Okay. So the next analysis that we did was trying to investigate if there's like a disparity in exposure with regards to income. So we first wanted to see whether we can do like an income-based site comparison. So just considering the sites of highest income and the highest of the sites of lowest income. And we use 2 indicators of socioeconomic status, per capita income, as well as person population below poverty line. And the next analysis we did was to see if there's going to be a relationship between the median pollutant concentration and the per capita income. So we looked at the Pearson correlation coefficient to just see if there's going to be if we can see like the strength and the directionality of this relationship. And then to further explore this, we used a simple linear regression model with median pollutant concentration as the response variable and the per capita income as the explanatory. And then next we did a non-parametric test, and this was done after studying past literature, and we were hoping to see the significance of the difference in concentration between groups of high income sites and low income sites. So what we did was we took the median income and kind of separated every site that's above that high income, we're going to group as high income, and then below that medium as low income, and then observe those two groups, the concentrations of those two groups. Okay, so these are the results from the first analysis, which is the income-based site comparisons. This was just done for curiosity, just how these concentrations compare. So for CO, we kind of see that in comparing 2019 and 2020, in both the years, the low-income sites in red seem to have relatively higher concentrations throughout most of the day when compared to the high-income sites in blue. And then if we look at PM 2.5, we don't see like a clear trend collectively for low income and high income groups separately, but we can see that if you look at the high income sites, Cedar Isles Teen, and I believe Highland Park Middle School, those are the high income sites, and they seem to experience like a decrease in concentration when going from 2019 to 2020. Whereas we see the low income sites, Bruce Cuento and Hawthorne, kind of having a slight increase when going from 2019 to 2020. So these are just slight disparities, which is interesting to see. And then we looked at the association between pollutant concentration and per capita income. And from the Pearson correlation coefficients obtained, we see that the correlation is weakly positive or weakly negative. I just want to introduce like the titles here. So R 2019 just means that is the correlation between concentration during that year and the per capita income. Same goes for 2020 and 2021. And then this is the correlation of the concentrations over the entire period of 2019 to 2021 and the per capita income. And then our reduction is the correlation between how much of a percent reduction was there over the for median concentrations over the years 2019 to 2021 and the income. Okay, then we did the simple linear regression model, and the only statistically significant linear relationship that we saw was for NO2, which had a p-value less than 0.05. And then conducting the Mann-Whitney U test, we found that the p-value was greater than 0.05, indicating that there wasn't a statistically significant difference among pollutant concentrations of the groups of high income and the groups of low income sites. And then we did exposure disparity. We observed exposure disparities by the redlining grades assigned in the 1930s by the Homeowners Loan Corporation. And we just wanted to see if there is an association between sites in historically redlined areas and whether there's a relationship with the air pollutant concentrations there. So what we did was we looked at the University of Richmond's Mapping Inequality Project and kind of overlapped their maps with the sensor site map that we have and try to figure out which HOLC grade that each site falls into. And if any of the sites were outside the bounds of these graded regions, because it's been quite a while since 1930, so there has been change. So if anything did not fit in those bounds, we excluded those sites from the analysis. So accordingly, we found one site fell into the group A, which was deemed best for lending mortgage loans. And then group B had 11 sites, and then group C had 15. And then the red line group had 7 sites. And we excluded 11 sites from this because it didn't fall in any of the zones. And we also excluded the group A because there was only one site. So we just compared B, C, and D categories. So looking at this, overall, we don't see much of a significant difference, but if you look at like PM 2.5 here, you see that there is a slight disparity in median concentration maybe, but it's not that significant. And with CO, there's barely any difference. And then in O3, similarly, not much of a significant variation there. Same goes for NO2, and then SO2, and then PM10, you see slightly for group C, there's like a slight disparity there, a bit higher than the other groups, the median concentration. And then NO, and then slight disparity with group D, but then it's very, the values are not that significant. So to conclude, we looked at the seasonal and the daily trends of time variation, and then we were able to explain some of these using atmospheric chemistry and also like anthropogenic emissions, traffic routines, and such. And then looking at the COD values, we only found a strong spatial difference among site pairs for NO. And then looking at the CBPF, the conditional bivariate probability function plots, we were able to get an idea of whether the emission sources were local or whether it's long-range transportation. And we were also interested to see, it was interesting to see that there was like a seasonal variation, season to season for some of the pollutants. And we were also able to justify the pollution peaks that we saw in the summer for SO2 and NO2 through the distant emission sources or wildfires. And then through the power spectral analysis that we conducted, we were able to see that there are daily periodic cycles, half-month cycles, monthly cycles, and month-and-a-half cycles dominating this time series data separated into seasons. We also found, I think from the analysis conducted, we conclude that there is little to no correlation between median pollutant concentration and income for the, it should be 44 locations because we excluded one in the study. And we also conclude that there is no significant variation in median concentration levels among groups of different HOLC grades in our study. But this doesn't mean that this might be true for other locations. So the importance of this project is that all these data analysis could be replicated for networks that are located elsewhere. And maybe they can tell us whether these kind of disparities in exposure to specific air pollution exist elsewhere. So these are the works that were cited and used in this presentation. And for acknowledgements, I'm so grateful for Dr. Wang. He has been such a wonderful mentor to me. And I've learned so much from him. I thank him for his time, his patience and guidance, and also the endless encouragement. I want to thank Dr. Lee for making this collaboration with MPCA possible, and for the constructive feedback given. And I want to thank the committee members, Dr. Jiayu Lee and Dr. Sanjay Madriar, for taking time out of their busy schedules to go through my presentation and for their interest in this work. I want to thank my research group mates for they have offered me feedback during the group presentations and such, and for the motivation. I want to thank Ms. Jeannie and Ms. Jody from our department. Thank you for all your support, and they have made this department a welcoming place. I want to thank all the professors in our department. I've benefited from their courses and the opportunities that they have provided. And finally, I want to thank my wonderful parents and my wonderful husband for making all of this possible. And yeah, thank you all.
Thank you, Varuni, for your nice presentation. So here is what we're going to do. So we'll just open up for all the questions. So this doesn't limit to like the general attendees or the committee. Okay, so anyone have any question, then you can feel free to raise it.
Beginning. Happy to answer any questions.
Mhm. So yeah, maybe I will bring up the first question. So in the spectral analysis, you show some periodical uh, like features for some pollutants, right? So I think we discussed this before. So if it's one day, then it is um, we can explain that. It's just quite reasonable, right? You see those general daily feature of the concentration, how they fluctuate, and they might be related to the rush hours.
Yeah.
So how do you explain 15 days and 45 days, or 30 days? Are there, I mean, what might be the reason that's giving you these longer term of period features?
That's actually a good question and something I've been wanting to explore because so I thought about it like a season that would be about 3 months, 90 days. So while the cycles do kind of make sense, it would make more sense to see like daily patterns for these pollutants. So I'm assuming this might be, maybe it's the noise that's within the the power spectra plot, and I'm guessing because when I calculated like the top 5 dominating periodicities for most of the pollutants, you see the daily trend appearing for most of them under top 5. So I'm assuming this might be because of noise, but this is something I'm still working on in interpreting what the how these cycles are um, possible.
Mhm. So yeah, I think we have two questions from the chat.
Uh-huh.
So first from Dr. Lee. So how do you comment your results regarding the synergistic effects among the pollutants? So do they change similarly or differently? So I guess she's talking about the monthly trend, also the daily trend, right? So you
Uh-huh.
see some of the pollutants having a similar feature, but some not. So I mean, what are your comments on that?
So if I go back to um so I think these two plots kind of make sense to me. But the particle pollution for PM10 and PM2.5 might be from like the same kind of sources here. Um, and then NO2 and SO2, um, well, if I look at like the daily and we see like similar trends for NO2 and SO2 here. I thought this might be because of anthropogenic emissions, like the rush hours, the first peak here, and then kind of decreasing with photochemical activity happening. But then I'm kind of unsure about this, how to explain this peak, to be honest. But yeah, so it might be of like similar type of sources there, but the next part of this research would be to really explore like the actual sources in the Minnesota region and then kind of trying to make more sense out of these plots.
Yeah. So I would say maybe for the NOx and SOx, it should be coming from the traffic emission, right? Because in the gasoline, you have these trace elements, and
Yeah,
then this is not related to photochemistry. I would guess it's less related to photochemistry
yeah,
because photochemistry affects the ozone,
yeah, I
right?
think the
So
SO2 is not going to be involved with the
mhm,
photochemistry because it'll be like a combustion emission.
mhm,
But for NO2, we know like the NOx and the VOCs are,
mhm.
yeah.
Okay. Um, So yeah, I think that's also a good idea to do some more analysis on the sources, identifying the sources of these pollutants. Yeah. So Weixing has a question too. So how might the approach used in this study be adapted to or applied to other urban areas facing air quality challenges?
Mhm. So I think we can similarly, like we did here, they can look at like the daily variations. They could do coefficient of divergence to see spatial variability. Now, basically all of these data analysis techniques that we've done here, especially the CBPF plots, might be extremely beneficial, especially if you have like a clear idea of like the region and the sources there. You can easily interpret, because this is just going to give you an estimate, but it can be a very useful tool for you to identify these, because you can identify the directionality and characterize it. So by doing some research, you can explore what these sources actually are. And the power spectra analysis would be great. And yeah, the income, obviously it's like a very, how would you say that? It might be like a very small variable compared to others like emission sources and stuff, but still you can do this and see like if there are certain populations being affected by these, like are they exposed to more pollutants, even though the pollution in the overall region seems to be good, and even if the pollution seems to be reducing, the emissions, they're steady and reducing, but still there can be like differences from neighborhood to neighborhood. So I think these type of analysis can be really useful to address like those disparities and the health impacts seen. I think you can even take a look at like impacts of COVID maybe by obtaining those health data. I think there's a lot of potential in these type of analysis. But I do want to highlight this at this stage, it's still an observational study, but and we haven't really established the causation of these. So
Yeah, I think so a related for and Dr. Lee has another question. Right? So it's about averaging the data. So how does the averaging tide might affect your data analysis? Do they put an impact on the data that you show here?
so averaging the data, the averaging time like into hourly and such.
Yeah.
Okay.
So for example, when you analyze like the monthly trend, right, and then plotting them, and then let's see, or the hourly data, or let's say for the exposure analysis, right? So for the income, household income. So do you average all of the data, or you average first into bins and then average it like first get a minute based and then average based on hours, or yeah, how will that data average might affect your
Yeah,
analysis?
those we just use like the hourly data, but I think it might be interesting to do. I've been wondering if I could do daily, um, like especially for like the power spectra and stuff. So that's kind of a work in progress. Yeah.
Mhm. Yeah, I think that yeah, on this side, I just recall, I think we had a discussion about the power spectral analysis, right?
Yeah.
So if you use the, let's say, in the extreme condition, if you use a daily average, then you won't be able to
Hello.
identify any daily trend, right? Hello?
Dr. Wong, I can't seem to hear you.
Let me try again. So can you hear me now?
Yes, I can hear you now.
Okay, yeah. So I think we had a discussion on this before. So for the power spectral analysis, if you think of the extreme condition of averaging data into daily bins, then you won't be able to see any like daily frequency in there, right?
Yeah,
Because you already average them out.
yeah, that is
So
true.
yeah, on that, so right now, how did we average the data? Did we use the minute based or use the hourly based?
We used hourly for now.
Okay. So, but the MPCA, do they report hourly or minute?
The data set reports in hourly, but the
Mhm.
readings itself, for every minute, the data should be available, but the data
Okay,
set has averaged for hourly.
okay.
Mm.
Yeah, maybe on that, we can try to use the minute-based data to see if there are frequencies in there. Right.
Yes, I agree.
Yeah, yeah,
Thank you, Dr.
okay,
Lee.
yeah. Any other questions? Okay, so if not, let's thank Varuni again. So, and also, I think now we will also excuse Varuni. So, Dr. Lee and are going to discuss your thesis, and then we're also going to fill out the rubrics, right, to evaluate your thesis. And then we'll also share this recording with Dr. Madura so he can evaluate you.
So,
I think you will be able to hear back from us either late tonight or tomorrow.
okay, thank you. Thank you all
Yeah.
for your time. I appreciate it.
All right.
Bye-bye.
Thank you, everybody.
Bye-bye. Thank you.
Bye.